that they're just two slits that are gonna be acting like sources. And you have a wave coming in like this, right? That shines on both slits. The wavelength is lambda. Right? I'll just represent the wave that's incident on these two slits with the wavelength lambda, and the distance between the two slits from the center of one slit to the center of the other slit is called d. So d is the separation distance between the two slits. And the slits are very narrow, very small. Very small compared to the separation between them. And some distance away is a screen. A viewing screen. Okay? And this point over here, right? This line over here, r is the distance between the two slits and the screen. And this line over here is perpendicular to that, is perpendicular to this, and this point over here is right between the two slits. So this distance is d over 2, this distance is d over 2. I don't like that notation with a capital R. It makes me think of a radius. I tend to call it capital L, but let's just stick to the notation in the textbook. It'll be easier for you to, it's easier for me to adjust to the notation in the textbook than it is for you to adjust to my notation and the textbook notation. That may drive you nuts. So, if the light travels through these two slits, and I look at this point over here, is it bright or dark?
Right?
Why? Why do you say it's bright?
Because from both slits, they have the same path length. Therefore, the path length difference is 0.
Exactly right. The two light waves going through the two slits, right, are going to travel exactly the same distance to that point. R1 and R2 are the same. So what's the difference between the lengths of those paths? 0. And I erased it, but if you look at your notes, if the path length difference is 0, it'll be bright. So right at the center, it'll be bright. And this is, I'm gonna label the bright spots like this. I'm gonna draw like a rectangle, but there's, So this is called the central, because it's at the center, right? From symmetry here, but then it's bright. And people call it also maximum. Actually, the word maximum is redundant, because if it's bright, it's a maximum. But it's called the center bright maximum. By the way, what's the value of m? That corresponds to a path length difference of 0. Look in your notes. M is? Zero. What's this, right? For 0 path length difference, m is 0. Yes. I'm gonna, how about I copy the results over there so you can refer to it. M doesn't mean mass in kilograms, right? We're not talking about mass. So, erase this. Okay, so bright means constructive interference, right? So that means that the path length difference, R2 minus R1, is m lambda, right? And the phase difference is, what was it, 2m lambda? And remember, m is 0, 1, 2, 3, 4, blah, blah, blah. Huh? That should be pi, thank you. So we have this 3 for bright. And then for dark, we have delta, or R2 minus R1, is m plus a half lambda. And the path length difference, I think we wrote it as 2m plus 1, right? Pi. And m is the same thing. See, 0, 1, 2, 3. Yeah, I think this is correct, right? Thanks. Yes, is that what you have in your notes? Okay. Now, that's because this distance is the same as this distance. And because they travel the same distance, the difference in the paths traveled is 0. And that satisfies this condition. In fact, let's write down some numbers or a few of the values. This would be, if the path length difference is 0, it'll be bright. If it's lambda, it'll be bright. If it's 2 lambda, it'll be bright. If it's 3 lambda, it'll be bright. Any one of those will be bright. Now this one here, I'm not gonna have enough room, so I'll make myself some room over here. So if this equals half a wavelength, 3 half wavelengths, 5 half wavelengths, and so on, it'll be dark. And then delta phi is yep, and then same thing for m, right? I think I use prime, so just let me be consistent. So 0, 1, 2, 3, so on. Okay, so if I look on the screen, at this point, the path length difference is 0. And that satisfies this. So it's bright. Now, what happens if I move off from the center? As I move off from the center, one distance is getting shorter and the other one is getting longer. If I look over here, for example, which distance is going to be longer? The one, which path length is going to be longer? The one for the light that went through slit number 2 or slit number 1? Number 2. So R2 minus R1 is not going to be 0. And as I move off over here, that path length difference is going to get longer, 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 longer. The difference, longer, 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 right? Now, here the path length difference is 0. Which condition am I going to meet next when I move off from the center? Will I get to a path length difference of half a wavelength or lambda or a wavelength? Half a wavelength, right? So it'll be dark. So next to that bright, there's going to be a dark spot. So I'm going to use just a line for dark. Now, what do you call that dark? You call it the first dark fringe line. So words that are used above the central bright maximum. And what is the value of m prime for that? Because now we're talking about the dark ones. What's the value of m prime that gives you that first dark?
0.
0, correct? Can you see that I get this in my path length difference if I choose this value? So that m prime is 0. So we have a dark one. That would be this one here, right? Now, as I continue to move off from the center, will I get to a path length difference of 3/2 lambda or lambda? Which one am I going to get to first? Lambda, which means I'm going to get a bright one spot. So next to that dark, there's going to be a bright spot. And again, I'm using like a rectangle to represent bright. So that's bright. And what do we call that one? You can call it the first bright fringe spot line above the central bright maximum. So, first bright fringe above. Obviously, it's above the central bright, which is the one in the middle, right? Maximum. And by the way, what's the value of M for that one?
1.
1. So it's also called, another name for it is the first order maximum. I'm sure you're running out of space in your notes. I have an advantage because I have the whole board to write that. But I know you're probably struggling to trying to squeeze in all that information in your notes specifically. Yeah. Yes? If I keep moving up from the center, then the difference in the distances traveled by the waves is going to get even longer. So what am I going to reach next? Am I going to get to 2 lambda or 3/2 lambda?
3/2.
3/2 lambda. So therefore it'll be dark. Which means I gotta draw another line like this. So it'll be dark. Okay, so what would you call that one? It's the first dark, second dark above the central bright maximum. So this is called the second dark above the central bright maximum. Right? And this corresponds to M prime equals to what? What is the value in this formula? What is the value of M prime that's going to give me 3/2 lambda?
1.
1. And we can keep doing this. I'll do 2 more. If I keep moving off, am I going to get to a path length difference of 5/2 lambda or 2 lambda? 5/2 is 2.5 lambda. Or 2 lambda. 2 lambda, which is going to be bright. So I'm going to throw the next one, it's going to be bright. So that's bright. And what would you call that one? Well, this is the central bright maximum. First bright above, second bright above, right? So you can call that the second bright fringe above the central maximum. And that corresponds to what? To M equals, what was the value of M? In this here, that corresponds to 2 lambda. 2. So this, because M is 2, this is called the second order maximum.
Are those the only ones, like the dark spots, are they called like first order or something like that? Those are just the only ones?
So one has to be very careful, and that's one reason why I'm writing this. I want to write one more dark, because you're beginning to notice something that you have to be very careful about. you're reading a homework problem, a quiz problem, a test problem, and it tells you, okay, something, blah, 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 blah. They ask you something about the second order maximum. So second order maximum, that means M, it's a maximum. So you want to use the equation having to do with bright spots, right? So second order, that means M equals 2. Yes? Second order, M equals 2.
Second order is 3.
For the bright ones, right? So second bright, M equals 2, second order. But, so it's easy with the bright spots. If they say, what is the distance from the central bright maximum to the 20th order maximum? Then, okay, 20th order, so M is 20. So use the formula for bright, because it's talking about bright spots, but then 20th order, so M is 20. Now, notice that with the dark spots, you have to be careful, because you don't call this the central dark maximum or something, because there's another one over here, that's not at the center. So this is called the first dark, because it is the first dark above the central bright maximum, but notice how the first over here doesn't go with M prime equals 1. It goes with M prime equals 0. And then it'll say, if they want to talk about this spot over here, they'll say the second dark spot above the central bright maximum. So it's the second dark, but notice that in that case, M prime is not 2, it's 1. So if they ask you a question like, the 19th dark spot above the central bright maximum, what's the value of M prime? 18. And if you put in 19, bad mistake. So with the bright spots, if they say the 40th order, M is 40. If they say the 17th order maximum, M is 17. But with the dark ones, if they say they're not going to call it the order, but they're going to say like, the 10th dark above the central bright maximum, M prime is 9. The 5th dark spot above the central bright maximum, M prime is 4. So just because if I were to do the next one, this would be dark, right? So this would be 1, 2, 3. So it's the third dark fringe or line. Sometimes they say line above the one at the center, which is the central bright maximum. But that corresponds to this one where M prime is 2. So notice that M prime is 2 goes with third dark. So one has to be careful with the dark spots. And that's why I'm taking my time to write all of this, all of this description over here. So you would see that for the bright ones, first bright, M equals 1. Second bright, M equals 2. If I were to do the third bright, M equals 3. But for the dark ones, first dark, M prime equals 0. For the second dark, M prime equals 1. Third dark, M prime equals 2. Right, so that's an important point to be made. These are just, so if you look at, and by the way, what you get above over here, because this is very symmetric, right? You got the wave coming in like this, right? This is very symmetric, right? You're gonna get exactly the same thing below. So this would be the first dark below the central bright maximum. And then the first bright below, and the second dark below, blah, 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 but it's just the same. And they tend to call this, like for the bright ones, they call this M equals 0, M equals 1, M equals 2, and then M equals minus 1, M equals minus 2, but I don't use the minus signs. It's just, you'll see that you don't have to use that. Yes? So, these problems tend to be very easy because So you're gonna get a just symmetric above the central bright. You're gonna get a dark, bright, dark, bright. So bright, dark, 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 and so on. It'll be symmetric. And usually the question deals with the separation between them, how it relates to the distance from the screen to the slits, and to the separation between the slits and to the wavelength. So there are 4 distances in there that are, there's a relationship between them. The wavelength is a distance. The distance from the slits to the screen is another one. The separation distance between the slits is another one. And then the separation between the slits is another one. And I want you to notice something. The distance that you really need to know, because you have complete symmetry on the screen, if you know the distance between this bright and this one next to it, or this one next to it, if you know the distance from here to there, let's call it delta y. I'm thinking of this like a y-axis, right? Let's call that distance delta y. If you know that distance, then you know the separation distance between all of them. Because all the separation distances are the same. Like this distance is going to be the same as that. And the distance from here to here is going to be the same. And if you have another bright over here, the distance from here to there is going to be the same. And if I go to the next over here, it'll be the same. And if I draw another bright over here, it'll be the same. And guess what? What if I consider the distance between this dark and an adjacent dark? It'll be the same distance, right? Because the dark ones are right in between the bright ones. So the distance between them will be the same because the other ones, and if I consider this distance, it'll be the same. If I consider this distance here, it'll be the same. This distance will be the same. This distance will be the same. This distance, the next dark over here, will be the same. So the thing to know is the separation distance between any 2 bright spots or any 2 dark spots. Now, we can derive what that distance is, and we can also remember it. The way that I remember it, so that I don't have to do the derivation, the way that I remember it is like this. I say, notice that this distance is horizontal, lambda, and this distance is horizontal. The distance from the slits to the screen, right? And this distance is vertical, and this distance is vertical. So if I multiply the 2 horizontal distances together, and I set it equal to the multiplication of the 2 vertical distances together, so lambda r is equal to d delta y. So if I solve for delta y, it will be lambda r over d. That's how I remember it quickly. Because if I memorize lambda r over d, d r over lambda, r, I'll put the lambda where it doesn't go and the d where it doesn't go, and if I just memorize it tomorrow, I won't remember it. So the way that I remember it quickly, it's just a way that I came up with so that I would always remember it, is, well, you got 4 distances, and just multiply the 2 that are horizontal, set it equal to the multiplication of the 2 that are vertical, I'll another line, boom, and I got it. So for example, you're solving a problem, right? Let's say you're solving a homework problem, and it tells you, what is the distance from the second dark fringe below the central bright maximum? Second dark below. So that means from first dark, second dark, to the third bright above. 1, 2, 3 to here. What is this distance on the screen? Well, delta y, delta y, delta y, delta y, half of delta y. 1, 2, 3, 4 and a half. That's what it should be. And delta y is this. Yes? Now, you can do it mathematically, right? But you'll just have that. And let me show you a picture of what the fringes look like, the dark and bright fringes look like after like going through two slits. Would that help? Okay, maybe that'll help. Maybe it's not necessary, but. So here you see the fringes are like on that screen. Of course, this is like an animation, right? For some artists, here they are. So m equals 0 is the center of prime maxima. That's this one right here. So notice that this is between, they call this m equals 1, m equals 2, 3, 4, 5, and then minus 1, minus 2, minus 3, but I don't use the minus signs. But I mean, you don't have to. And then notice that if you take any two adjacent bright spots, any two, it's the same distance. And by the way, take any two adjacent dark spots, like those. Right? That's the same as any two bright, any two bright, any two bright. It's any two adjacent darks. It's you have this symmetry, right? So if you know the separation distance between any two adjacent bright or any two adjacent dark, you can figure out the distance between any of the other ones. It's like a ladder with the rungs, you know, at the same separation distance from one another. So how do we derive that expression that the separation distance between them, between two adjacent bright or dark spots is, what was it, lambda r over d? How do we show that? How do we do that in mathematics? Okay. So here's how I'm going to do it. So we're supposed to show that. By the way, notice that delta y is the following. What if I call, you know, like a y-axis like that, and I think of this as an x-axis. Suppose I think of this like an x-axis. So what's the value of y on this x-axis? So notice that delta y is the distance to the first bright. It's this, right? It's y, the first bright with m equals 1. That's just delta y, right? So if I get the distance to the first bright spot above the center bright maximum, then since they're all the same, then I have all. I need to show that that is equal to this, or that delta y is equal to lambda r over d. So one way to do it is like this. So consider the two slits, right? And the distance between them is d. You have a wavelength. I like to draw it like this, right? Lambda. And then you have a screen over here, some distance r away. And I will consider, in general, so this is the screen. I will consider a spot over here. This is y equals 0, so therefore this distance over here will be y, correct? I'll just call it y. Bright or dark, I'll just some spot on the screen. And light is going to go through that slit to there, and then, right? And then light is going to go from this slit to there. If I want a bright spot for constructive interference, maximum reinforcement, bright, then the path length difference has to be 2m lambda. Correct? It has to be that. I'll just call it delta. So delta has to be,
It's just M lambda, isn't it?
oh, yes. Thank you. M lambda. Okay? Now, I'm going to say the following. I'm going to use an argument that usually these distances, I mean, the screen is far away from the two slits. The two slits are very close to one another, like really, really close. So, if I draw, I mean, what is the extra distance that one wave travels compared to the other one? So, if I draw a line like this, right, and suppose I say that that distance is the same as this distance, then the extra distance that one wave travels relative to the other one is going to be this. And I'll say that this one is such that this is roughly 90 degrees. So delta is going to be this piece over here. And it's like I'm saying these two points are at the same distance away from there. So if this angle is theta, what is this delta? If you look at this right triangle over here, notice that this is the hypotenuse. What is this distance over here? I have this, which is d. I have this, and then I have that, with this being 90 degrees, and this is theta. So what is this distance here? D sine theta. Yes? D sine theta. Now, from geometry, we can show that if I draw a line from the center over here to that point, the angle that this line makes with the horizontal is also theta. So let me show you that. But I need to, can I erase this part at least over here? If let me draw this, let me draw, so this point is this. And then I'm gonna go here, which is this. And then we have, this goes like that. And then this line, in fact, let me draw it big. There's no need to do it so small like that. Right, so then this goes like that, right? And then this line goes to that point, so this is theta, right? But if I go like this, and I make that 90 degrees, right? And this is theta, so what angle is this? If I look at that triangle, 90 minus theta, right? But this is 90 degrees, so this angle must be theta. So that this angle added to that gives me the 90 degrees. Can you see that? I mean, put in some numbers. Suppose this is 30 degrees. That makes this 60 degrees. So therefore this has to be 30 degrees, which is the same as that. And from this geometry over here, what if I take the tangent of this angle theta, of this theta? So the tangent of angle theta equals, the tangent of this angle theta is going to be y, if I look at this right triangle now, right? It's going to be y divided by r. Yes? But the path length difference can be written as d sine of theta. So this is geometry. And this sine theta is also geometry, right? Now, if I want to consider a bright spot, because I want to know that this is, if I want to consider a bright spot, Can I erase this now? If I want to consider a bright spot, then I'm going to say, okay, from geometry I have that the tangent of theta is y over r. Now, and delta is d sine theta, right? So both of these are geometry. Now, physics. If I want a bright spot, then delta has to be m lambda, right? And now with m, so delta has to be this, right? For bright, with m being equal to these values. So now what I'm going to do is, with m being 0, 1, 2, 3, blah, blah, blah. So that's this part over here is the physics, right? So now I'm going to take this and I plug it in here. That means d sine theta equals m lambda. Now, but these angles, like I said, you're going to have two slits that are like, they're like far away from one another, like the thickness of a hair, or 2, 3 hairs. So they're very close together and you're looking very far away. So these angles that I draw over here very big, these angles are small. But for small angles, the sine of theta is approximately the tangent of theta. Right? Take the sine of 1 degree, get a number. Take the tangent of 1 degree, you essentially get the same number. Take the sine of 2 degrees, take the tangent of 2 degrees, they're roughly the same number. So therefore, this approximates to d tangent of theta, which is m lambda, but then the tangent of theta from geometry is this. So this is d times y over r equals m lambda. So the values of y on that screen that give me, and this y over here is for bright spots because I use this condition. The values of y that correspond to bright spots will be m times r lambda over d. And I tend to write this like this. I write y right. And notice that the value of y on the screen from the center bright maximum depends on what value you put in for m. So if you put in, for example, if I want to know this height over here, for that spot, m is 1. So if m equals 1, then y1 equals r lambda over d. And that should be this. And in fact, if I say, well, how do you know that the distance between the second bright and the first bright is the same as the distance between the first bright and the center bright maximum? Or the distance between this and this is the same as that one? How do you know they're the same? Well, we can just say this. Okay, what's the separation distance between bright spots? Son of a gun. I'll just finish with this. So if I say, okay, what's the separation distance between the bright spots? Well, it would be adjacent bright spots. It would be y of m plus 1 minus y of m for bright and bright, right? In other words, this is for any bright spots. But if I want two adjacent bright spots, if m is 20, the next one is going to be 21 or 19. If m is 15, if it's adjacent, the next one m is going to be 16 or 14, right? So if one is m, the other one is I'll just make it m plus 1. So what is this separation? What is the value of y for m plus 1? Well, I just make m plus 1 over here. So it would be m plus 1 r lambda over d. Minus, now, what's the height from the center bright maximum to the bright spot for the order of that? It would be m lambda r over d, right? And if you multiply this, if you expand this over here, you get m r lambda over d plus r lambda over d minus m R lambda over D, and this cancels that, and you get that it's, R lambda over D. So, they're the same. If they're adjacent, it's the same. And if you do, you can derive an expression for the values of Y on the screen that would give you dark spots. And the only difference is going to be that this is going to be M plus 1. M plus a half, actually, M plus a half. Actually, and I call it M prime plus a half. So, I'm doing this as just algebra, geometry over here, doing the math, right? But the thing to know to actually answer problems and so on is this. If you remember this equation, you can answer almost any question related to this. You can take this shortcut and figure this out, and then from there, if you know what the name of each fringe is, then you can work with it and get answers. Let me ask you this question before we go. This is anyone here planning on taking the MCAT exam to go to medical school? No, okay. Well, typical MCAT exam question. It's an exam that people take to go to get a score and then compete with other people who are applying to medical school, right? And there's a part that has to do with physics. And I remember a former student of mine came to me and said, who was going to medical school, this question came up, and what's the answer to it? So the question was this. Light comes in, 2 slits, and if you look at this spot over here, what's the phase difference between the 2 waves that arrive over there? What's the phase difference between this one and this one? It's bright. So what are the only possibilities?
It's in phase.
Which means, what are the values?
So 0,
0,
2 pi,
2 pi,
4 pi.
4 pi, 6 pi, 8 pi. So 0, 2 pi, 4 pi. The answer is 4 pi. What about? What's the path length difference between these 2 waves when they meet over there? 0, lambda, 2 lambda. Or you can say it like this. Well, that's m equals 0, m equals 1, m equals 2, because it's bright. M equals 2, phase difference. 2 times 2 is 4 pi. Path length difference, 2 lambda. But it's more of a conceptual question, right? If you understand what, then it's a lot easier if you kind of understand the concept than trying to plug numbers into some formula and trying to figure out what the path length difference is, or, those are questions that are based on the concept, and you don't really have to do a calculation. It's like either you know it or you don't. Okay. We'll meet for lab.